We're just talking into the mic.
You're
here.
live. Yeah, just.
Okay. Hey, George. I'm gonna turn that off. All right. So if you guys can pull up the GitHub and you can kind of follow along. Let me just turn this off. Okay. So we've talked about GANs for almost 3 hours already. So we're not gonna deal with a lot of the theory right now, unless you guys like have questions. But that's one of the good things about kind of having a smaller crowd on Friday morning is if there is something you guys want to talk about, just shout it out. So we're gonna go straight into code, and we're gonna try to walk through literally every line of these files that implement GANs. So like, people have had a lot of random Python questions. You don't know how the import statements are working or something, definitely ask now, because we don't, we want to cover all that stuff here while we get a chance. So with that said, today we're talking about GANs. In Recitation 10 folder, you'll see the notebook. The notebook doesn't really have any code in it, but it links to the rest of the code. You have a question? Sorry. Okay. But anyways, so we're going to build some GANs. We're going to do them in Inferno. Okay, stream. I hope we're back on. The internet dropped on the surface. Things happen. So anyways, we were starting to look at the MNIST GAN, and so function number one. And when I said we're going through the file, I really do mean I want to explain each line and make sure you guys know what everything is doing. So this is the MNIST data loader. Pretty straightforward, just pulling in from the data set. The key things to keep in mind here are I have my KW args here. So that is telling it to have loaders that are getting the data and pinning the memory and getting it all ready to go over to CUDA really nice and efficiently. We're telling it to, right now we're just dealing with the trained data set because we're dealing with the generative model. Validation isn't really... that validation is a whole other story, which we talked about in lecture. So for right now, it's just the training set. And otherwise, I'm just pulling in some items from the arguments. So any questions about the data loader so far? Just the first function, starting simple. Good. Here we have the initializer. This is similar to what we've seen in a lot of other homeworks. We're just running Xavier, and we're on anything that's a weight, and we're zeroing anything that's a bias. So you should have seen that stuff before. Here we have something that's a little more interesting, which is trying to format images into an image grid. So what this function is trying to do is to produce a grid of images that can be displayed as a single image. So it's taking a list of 100 images and making it into a 10 by 10 grid of images. So we can circle back to specifically what the outputs look like. But basically, this is the set of transforms. What you'll see here, when you run this code, it will both log to TensorFlow or to TensorBoard, and it will actually save out a video of what your training looks like, and we'll loop back around and actually look at the results there. But it would be worth mentioning things like the absolute path and the current working directory. Hopefully everyone understands what current working directory is and how that kind of affects how your programs work. But basically every program, every system, every process that you're running has a directory that it's currently in. And when you give a path that doesn't start with a slash, then that means the path is relative to where that current directory is. So a lot of people got confused on working directory issues when they were dealing with homework. Well, really all the homeworks actually, but you should understand how the working directories work for like relative paths and relative imports. A couple posts on Piazza, but definitely keep that in mind.
So you said when you give a path that doesn't start with the slash, it treats it as relative.
Relative to
starts with the slash.
Starts with the slash. That in Linux that would mean start at the beginning of the directory during the system, and then in Windows, if it starts with a backslash, that means start in the beginning of whatever drive you're currently on. So there's no like root of a file system, but if you're in like C program files, then backslash whatever would mean C backslash something something. Right. Right. So a lot of like, obviously this is not ML, this is engineering, but I know not everyone here are engineers, so definitely ask questions if you have even non-ML related questions. This next one I definitely want to mention, which is saving the arguments. Super important. You guys should try to put something like this into every script you run. In terms of what it does, it's actually just saving your command line arguments to a file each time you run the script, so that you run the script 10 different times, you can look and see what your arguments were each time you ran it. That's really important because I'm putting my hyperparameters into my arguments. So what that means is I run my script 5 different times with 5 different whatever hidden dimensions or learning rates or something like that. Then I've got 3 different folders with each of the different runs, and each of those folders has the exact parameters that I use to make that run. And this is the type of organization that I've been talking about a lot. And basically, you start doing things like this, and you can really keep track of what you're doing, and then you can make informed decisions as opposed to just guessing hyperparameters and hoping things work out. So in terms of the code itself, it's just, this is making directories. The exist OK is a Python 3 only flag. It means don't crash if the directory exists already. And then it's opening a new file. We use ospath.join when we want to make file paths. That is the correct and OS independent way. You basically give it multiple parts of a directory and it joins them using the path separator. And we're opening it in write mode. As I said, I'm covering every line, so if you guys are confused about how opening files and writing works, please shout now. So basically, we're opening the path. We're creating a dictionary. So var args is turning the argument object into a dictionary object. .items is going to iterate through each key and value in the dictionary, and then we're just writing them out with an equal sign. So what you expect when you run this code is everything you gave it on the command line and everything you didn't give it, so it'll just write out the default parameters, all get written to a file, and then later on you don't get confused about what you did when you ran that file. You actually know what you did to run your code. Okay. I know these are bits and pieces, but we'll see them all kind of come together in a second. Here we have a pretty simple module, which is just a reshape. What it does is it just reshapes the input to another shape. That is something you guys typically will just be doing in your forward function, but when you do it like this, you're suddenly working with object-oriented code, and you can start using things like a list of modules. You can use sequences. It's a way to organize your code as opposed to just writing into your forward function, do a view in between 2 layers. So it's a very simple module, but you guys should understand how to write modules for whatever it is you want to do. And you also should understand things like the star syntax. So the star syntax means you can give it however many parameters you want, and all of those parameters go into an array, and then that array is called shape. And then here in input.view, that means shape is an array and its parameters are kind of all written out into the function. So it has 3 items in the array. It's going to actually pass 3 different parameters to the view command. So this is how we kind of work with the view command. You'll see things like this very frequently, view star something, and that's because the way the view command works is it doesn't work like NumPy where you give it like a list of shape. You actually give it multiple parameters, a parameter for each dimension. And because that's kind of ugly, you'll have to use the star syntax very frequently. Any questions on star syntax? Or something?
It is passed as a list.
I'm sorry?
It is passed as a list or a tuple.
Yeah.
It's the list.
Yeah. Yeah, it's a list or a tuple, but you can expand it out to pass it in parameter-wise. Okay. So we'll see actually why we have that reshape, and that's this generator network that we put together right here. So our generator network, we actually had a lot of questions about how inheritance works. So this syntax here means that my generator network inherits from the class NN sequential, which is a class that is predefined by PyTorch. So I'm using that because my class is just going to be a list of modules, and by deriving off of that, I can save having to write my own forward function. Now you see a little bit of funky syntax here, and that's actually another star syntax. And that's because sequential doesn't take in an array of layers, it takes in a layer for each each parameter to sequential is a different layer. So that means you have to kind of splat them out. That's actually the splat operator is what it's called. So we use the star. So kind of, I want to unpack this kind of funky looking syntax for you guys to understand. So this part here is making an array, and you see that I've done it this way because I'm going to enable or disable batch norm depending on whether I want to have batch norm here. So what I'm doing is some elements of the array might be none if batch norm is disabled. And that's that inner array. Then there's this outer array which goes through the inner array and skips the part where m is not, well, it only includes the ones where m is not none. So the way I'm giving a variable length array, and I'm creating that variable length array without having a bunch of independent if statements with like appending to a different list, it's a kind of smooth way of creating the array, which might have some nuns in it, filtering out the nuns, and then giving those nuns to sequential. So after I create that array, it then gets splatted, so that will create a different list of arrays depending on, it'll create a different list of modules depending on whether or not this if statement evaluates to true or false. So in terms of our actual generator network, this is the generator. That means we give it latent dimensions, and it gives us images. This is the probably most important part of a GAN. So in terms of what it's doing, we're basically we have some linear layers at the beginning, and after our linear layers, we're going to do some convolution transpose layers to do the last parts of the network. I don't know if you guys have, well, we've shown you videos of convolution transpose, but you guys might not have been paying attention. So convolution transpose is basically the opposite of convolution. It's not really, but it's close enough for our purposes. So it's kind of like by having strides in convolution, you make things smaller. By having strides in convolution transpose, you make things bigger. So that's why we're using convolution transpose in our generation, because you're kind of building a invertedly shaped convolutional pyramid. It's getting larger to fill up the image as opposed to starting at an image and getting smaller to, give you a label or something like that. So we basically, there's a very standard way of doing things, is you have it's really the inverse of what you do with a fully connected layer on top of a CNN. And that's basically that you design some linear layers, and then your linear layer basically, it's this guy here. So this block right here is actually just one image from the point of view of your code. So we come with a list of like 100 images, and I'm just reshaping those images into one image so that it looks nice when you look at them and you can look at 100 things at the same time, or whatever it is.
So the generator discriminator is only a single image at a time?
Right. Well, it's looking at a batch of images. So like the network, like each thing is independent other than batch norm, which makes things not independent, but that's another story. But it's making a decision based on one thing, but you haven't seen any for loops yet. That means we're doing the entire batch of real at once, the entire batch of fake at another time, but they're both running them all at once. So anyways, this is just the generation. So this latent, the size of latent is going to be n by the latent dim, and the outputs is going to be n images. Okay? And then the corresponding function we have is discriminate, and that just calls the discriminator on an input. So these are the two kind of fundamental generating and discriminating functions that are just calling the generator and calling the discriminator, and we're going to use those in the rest of the GAN model. Okay, this function is the calculation of the outputs for fake. That's a combination of two things. That means run the discriminator on the generated outputs. So that's what this chain here means. Why fake is discriminate, generate, latent. Any questions about that line? That comes straight from the definition of kind of what a GAN is, and that's why it's there. You were running the discriminator on the generator, and we're going to use that fake in the rest of our loss function, things like that. Okay, next we have why real. This is just running the discriminator on the real inputs. Pretty straightforward. That's the flip side to why fake. We tend to call them fake and real just because those are both 4 letters and it makes your code nice and lined up, but you can call them whatever you want. And then here we're also saving the real data for later. So far we've got the real data and a grid of the real data, and we've got the fake data and a grid of the fake data all saved out to our state hooks for later.
Question.
Yeah.
So are you saving all images from the training set or
This is each batch. That batch gets saved. And then later on, we're going to see the configuration where each batch can get uploaded to TensorBoard for logging. So the state hooks are part of the TensorBoard part. I'm actually doing 2 different logging of images here, which we'll see. One is dumping images to TensorFlow or to TensorBoard so you can have like a live view of them. The other one is I'm saving them out to the disk so I can run MPEG so I can actually make a video of them. Obviously, you could just do one or the other. It kind of depends on what you're trying to do, but we've coded both for you. One more part of this is actually generating the latent sample. This is important to understand how things like data and new work. So xreal.data.new means you're creating a new tensor that's the same type and the same place as xreal. So if xreal was CUDA, that would make a new CUDA tensor. If xreal was CPU, that would make a new CPU tensor. Make sure you use .data.new as required. We covered it in the second lecture, but you'll see it come up again and again. We then create some random variables and we use the out, and we point the out to latent. So these 2 lines are the kind of thing you'll do a lot in PyTorch, which is basically you allocate some data, and you allocate some data using data.new so that you know it's in the right place, and then you call whatever function giving an output equal to that thing you just created. So the combination of those 2 things, in this case I'm just using it to make some random normal tensor, but the general idea of calling new and passing it as the out of the next function is going to occur a lot. Then we wrap it in a variable because, of course, it needs to be a variable, and we return it. So overall, this function is just creating latent samples that are the same size as xreal. Point looks like over time as opposed to things jumping around. So it's going to make our videos actually make sense as opposed to being just a bunch of noise. And then last but not least, we've got everything written. We can actually run our model. So in terms of running our model, loader, first thing first, save your arguments so you know where they are going to be next time. Create your train loaders, create your model. This is the actual trainer itself. Mostly the same as before, but you'll note that we are registering the callbacks here. So the generate data callback we've added and the generator training callback we've added. We bind the loaders, we create the loggers, and one other thing that's different than before is we're adding these observe state lines. What those observe state lines mean is basically you should log these things. So in order to log an image, there are 2 things you need to do. You need to have that state hook dictionary and add generated images there. And then when you create your logger, you need to tell it to observe state generated images. Between the 2 of those, that's what makes this part happen. And you see generated underscore images and real underscore images are these 2 states that it's observing. Otherwise, CUDA, main, just setting up argparse, and the if statement at the bottom. I will actually point this out because a lot of you got confused, had a lot of issues with just uploading your code in a lot of the homeworks, and that's because you weren't really wrapping your code efficiently. Note how this is a Python script. There is no unindented code that's not like def function or a class definition or an import. And you really want to have your script so it can be imported without running any code. When you import it, it should just define a bunch of functions. So what that means is this if name is main, that only runs if it's the main script. If you just import it, nothing runs. And the reason it's broken out like this is, see, main, this main function call passes the system arguments to the main function, and the main function here does its arg parse. The reason it does it that way is if you have another function or another file that you want to be able to use this file, you can both run it from the command line, but you can also directly call main. So the way that actually works in practice is you see kind of in the Pi notebook how to call it. So you can do something in your code like that, and when you run that, it's basically equivalent to running on the command line. You can imagine what it's doing, but that way you can write something that's a script and can run standalone, and at the same time can be used by other scripts. So that kind of flexibility and best practices is just something to keep in mind.
Question. On the logger of those states, the logger will try to find the hook, right?
There are two separate processes, which is when it's training, it will periodically look at the hooks and copy the hooks into the trainer. And then when it's logging, it's looking to see if the trainer has that state. So the trainer has like a state dictionary that it keeps, and the logger pulls from the state dictionary, and the state hooks push to that state dictionary. So it's a little bit indirect, but roughly, yeah, that's the way it works. And you can use that for anything. If like you have a regularization loss you want to track, and you want to track your average output, and you want to track like 3 other things, just add observe state for each of them, and also add the state hook for each of them, and then you'll just have a graph, and you can have graphs of different, like each run will have its own graph, and you can compare the graphs and everything about TensorBoard that I always talk about. But anyways, so that was a lot of code to walk through, but the final product that I think you guys all deserve now is this guy right here. So you'll see a lot of the kind of chaos, because this is the basic GAN. It's just the core GAN. This is what's actually going to be written out by your model. And I guess the audio died, but there's some nice audio to go with it. Okay. But anyways, so you'll see the way that it actually kind of spirals around and eventually starts to settle. And just remember what this looks like. Look at the video again if you need to. It's kind of mesmerizing almost. But you'll see the way that it wobbles. And especially the key part to keep in mind is at the beginning, that you see this kind of that effect. That is what GAN training looks like with the traditional GAN. And eventually it starts to catch on. And we're not going to watch the entire thing because I've got several videos. But by the end of the video, it actually does start to settle down, and you see the numbers forming to, those look like MNIST digits. And that is what our code so far produces. Looks nice. But what we'll see is I spent a lot of time kind of figuring out the hyperparameters that would work the best. So if we compare that to this one, which is, see, when I ran this, I changed the generator frequency hyperparameter, and I changed the directory I save it to, and that means that save directory is going to have a file which says what the generator frequency is. It's going to have a separate graph. I can compare the graphs, so all of the logging stuff that I always talk about. Anyways, so with a slightly different generator frequency, you see completely different behavior, and that's because GANs are just not so... Oh, that one worked. It's kind of pretty. But yeah, this is what a GAN with incorrect hyperparameters looks like. I just changed one parameter, and that's the cyclical kind of weird behavior. This is so even if you have your code completely correct, everything's right, slightly wrong in terms of hyperparameters and settings, your GANs will actually give you nothing. So that's the kind of thing to keep in mind with GANs, that when they work, they give beautiful results. When they don't work, you can just end up with complete junk. Okay. So we're going to take a step up to something that's a little bit more stable. which is the Wasserstein GAN with gradient penalty.
Real quick, just curious, what was the parameter that you changed for that last?
It was the frequency that you train your generator. So if you train your generator, if you train your discriminator 5 times and your generator once, then it works pretty well. But if you turn that number down too much or up too much, then you get chaos. I turned it all the way down to 1, but there are a lot of hyperparameters. If you just want to try running the code and change like any parameter a slight bit, you'll see kind of the sensitivity. Like there's a little bit of leeway, but it's a very narrow valley.
What's your methodology around hyperparameters? Like, how do you know which to change,
Right.
other than like?
A lot of it's experience, a lot of it's having a lot of graphs, and the other side of it is switching to better models that are slightly more resilient, I guess would be a good word for it. So anyways, with that in mind, here's a more resilient model, which is the WGAN. So we already talked about what WGAN is. If you have questions, post on Piazza or whatever, shout them out. But you guys should know the theory already from the second GAN lecture. But in terms of the actual calculation, what makes it different is, number one, the loss is just...
Hey, Ryan, we good?
Okay. We lost the stream for a second, but I think we're back up. Okay. So we were looking at this thing right here. So this gradient is setting create graph as true because we're going to have to calculate the gradient of that gradient. And the loss that we're calculating is, this is the 2 norm of the gradient, and we're finding the difference between the norm and 1, and then squaring that, and that is actually our penalty. So in terms of why we're doing these calculations, definitely read the paper, or you should have asked questions during class. But in terms of how to do the calculations, that's what we're doing. We have to create a gradient in a special way so that we can then use that gradient into our loss. And then finally, our actual loss is just our original loss plus this penalty, which was a kind of pain to calculate, but that's how it goes together. And then in terms of the generator loss is nice and easy. It's just the negative expected value of y fake. That means your generator is trying to make y fake as large as possible, because if y fake is large, then its loss will be negative a large number, so it'll have very little loss. And then the run function is basically the same as before, but I've just swapped in WGAN for not WGAN. And now if I go back to our lovely set of videos, you can see the difference that something like Wasserstein GAN makes. So keep this in mind that this version is what the regular GAN looks like. That's what regular GAN trains like, right? Versus here is Wasserstein GAN, gradient penalty. Boop. Yeah, so really significant improvement. It pretty much goes straight to where it needs to be, but the real key part is this initial kind of thinning. But you see it very evenly go. You almost kind of blink and miss it. But you compare that to the weird little dance that the regular GAN does, and it just doesn't even compare. By a couple seconds into the video, it's actually looking pretty good. And if we were to, some of these have good audio, some don't. But by the end, you see some really nice, clean, awesome looking digits. That is our WGAN and why we use it. It is very possible to get it. I don't know why that one's next. If you like GANs, you might like political. Okay. But anyways, so that is our Wasserstein GAN. We're going to step it up a little notch. I think we'll be running just on time. So make things a little more complicated. We're moving up to the CFAR 10 GAN. So in terms of data loader, we've got basically the same thing, except we're swapping out CFAR 10, obviously. But this has made our network become a little bit bigger because it's a more complicated data set, and we're also using Wasserstein GAN, so we can afford to use more layers. I will say, by the way, that the Wasserstein GAN that you just saw and the original GAN you saw and the other GAN, which failed completely, are all exactly the same discriminator network, exactly the same generator network, exactly the same hyperparameters and learning rates and everything, except for the one place that it changed. It really is the penalty that just completely changes its behavior. So here we have a CFAR10 network, just for a good example for you guys of how to kind of organize your code again. Very similar, but the shapes are obviously going to be different. We've got more convolutional layers. We've got a bunch of batch norms to help clean things up. And our discriminator network is also going to look similar, but now we're going from 32 to 32 to 16 to 8 to 4 to 2 and all the way down to 2, and then from 2 we're flattening it out. And our generator is kind of the opposite. Our generator, we're making something that's 2 by 2 by 512, reshaping it out, and then convolving all the way from 2 to 2, 4 by 4, 8 by 8, 16 by 16, 32 by 32. So both of these would qualify as deep convolutional GANs, but this one's a little deeper than the other one. And then in terms of actually running it, again, we're sticking with pretty much the same training functions, etc. But the difference is now, obviously, we swap the data set and we swap the networks. And what we get with this, oh, sorry, that's the conditional GAN. That was not what I wanted to click on. CFAR10. Yeah, so now I've got actual images. I assume you guys know what CFAR10 looks like. But this is kind of just giving you guys experience of what GANs look like when they train. You see a lot of that kind of like flickering and getting slightly brighter, slightly darker as they slowly kind of morph into images variously. It's not the deepest network, but it is able to get pretty reasonable results on CFAR10. Remember, these are just like pictures of boats and dogs and streams and this, that, or the other. A lot of frogs in it, things like that. And it was only trained for about 50 epochs. It's probably like 30, 40 minutes of training. But by the end, yes, they're still kind of like blurry shapes, but better than your typical outputs. And of course, if you make a deeper network, train it for longer, things will end up being a lot sharper. And hot wings apparently is related. Cancel. Okay. So that is our CFAR10, and finally the kind of more complicated. So that was a more complicated data set, and we're going to spend a few minutes talking about a more complicated model. So this model is the conditional GAN. And you guys remember what the conditional GAN is? That means it takes inputs that are the labels as well. So it's not just learning to generate data, it's learning to generate data conditioned on the label of the data. So ideally it's something where you can say generate ones, generate twos, whatever, and we'll generate those. And we'll have a single network that can generate different digits based on what you're telling it to do. The reason that's more interesting, I think it's working.
It looks good, yeah.
Okay. Hello, stream. Sorry about that. So next up, let's see, where were we? Yeah, so this is a little bit tricky. We're just breaking this down. So embedded is n by embedding dim. We add one dimension, then we add two dimensions. So it's n by embedding dim by 1 by 1. And then we expand it so we don't change the first two dimensions. And the second and third, like dimension 2 and 3 being the third and fourth dimensions, are going to be exactly the same as x. So basically, we have added the extra dimensions, and then we've copied things out along those extra dimensions so that we've got a much bigger array than we started with, and this new array is going to line up exactly with our input x. So that when we concatenate them among dim1 is the channel dimension, we then have 33 channels instead of one channel because we added 32 extra. So anyways, that's how we put the two inputs together. One is the actual image versus one is an embedding of our label. And then that whole thing is what goes into our trunk being a bunch of convolutions and fully connected layers, yada, yada. So you see how those are very similar to our previous discriminator and generator network. I just added a C at the beginning, and they have this extra input. Now, how do we incorporate that extra input? It's basically, we have a CGAN model, which I am deriving from my original GAN model. And the difference you'll see in each of these functions is basically adding a Y at the end of everybody. So generate takes both latent and a Y, and it calls the generator on latent and Y, and it's storing the Y in the state hooks. Similarly, we have a discriminator. Discriminator now takes in a Y. Our Y fake now takes in a Y. And you see things like this, where when we generate Y fake, we both pass Y into the generator and Y as a function to the discriminator, because both of them are conditioned on Y. Similarly, Y real, I'm saying Y a lot right now, but Y word, now we see it takes in both X real and Y. And the reason, and this is the part that actually connects to Inferno, because Inferno has two inputs, it's going to pass two inputs to our forward here, and that's where we pick up. Discriminator loss is just slightly changed, overriding one of the functions to gradient penalty. So basically, if we have 100 inputs and the first input is a 1, then the first generated thing should also be conditioned on a 1. And then we're going to do a linear interpolation between those two 1s, and that linear interpolation is where we're going to discriminate. We're going to discriminate conditioned on it being a 1. So all of those things kind of line up easily, and by them all lining up, it's almost like we're training these separate GANs in parallel, but sharing the network that's doing all the work. Next up, our generate data callback, roughly the same, but the difference here is that before I just created a latent, and I had a latent that I hung on to. Now I both have a latent and a Y. And my Y is just going to be an A range, and the reason the Y's in order from 0 to 9. And otherwise, training iteration, generate, pretty much the same as before. I'm just passing in the Y that I didn't pass in before. Running it, you'll see it's very much the same. Of course, CGAN model and CGAN data loader as opposed to all the originals. Binding to loaders. This is one other important difference, is if you have multiple inputs or targets in Inferno, the way you handle that is this num inputs and num targets in your bind loader. So your return values from your data set or your collate function should be flat. So like if you have 4 inputs and 5 targets, you should just return a list of 9 things. And it should be all the inputs and then all the outputs. And when you tell Inferno that it's 4 inputs and 5, then it will check and slice things out appropriately. Otherwise, generator, logging, observed state, all that stuff's the same. At the end, I'm calling my little generate video function. And what that gives us here, if I go back a little bit. Okay, so now this is a conditional GAN we're training, just to show you guys how something like that would work. And what the conditional GAN ends up doing is, so it'll look a lot like the GAN WP, the GAN GP, but now you see that. Haha. Everything's actually organized and sorted out. So each row obviously represents one of your labels that you're feeding in when you're training everything. And that's it. You still see some waiver. GANs are not perfect, and hyperparameters matter a lot, but it seems to be doing what it's intended to do. And then by the end of the video, you see it kind of sharpens everything up and then takes us back to Jog. So let's cancel that. This is not my laptop or anything, by the way. I don't know what that's about. So that's the models I want to take you guys through. We got a couple minutes, so I just wanted to check that all of these make sense because they're kind of similar for all of them. The save directory is just where we're saving things. You guys should be passing that as a command line to every script you write. You should change it every time you run the script, and that way you've got a bunch of different versions. You can compare them all. As I said before, when you're in TensorBoard, and you've got stuff in a bunch of different save directories, then you can just click around and like compare graphs from different directories, and that's really where the bonus comes in. But I'm just going to run through these really quickly. Batch size is your batch size, epochs, how many epochs to run. This image frequency you see there is actually how frequent. Yay, GANs. GANs are fun. GANs are tricky. They're really fun to watch. They're really mesmerizing. You guys should play with them. So,
It's just like very technical, not very important, but like when you're generating the random numbers in Torch, I think you don't really have to pass a list, but you can pass like a torch.size or a tuple, and it works just as fine. So,
Yeah.
start on.
I think it depends on which PyTorch. There were earlier PyTorch versions where it would only take a list of, or would only take separate parameters and not a list. But I mean, I haven't actually checked. So
Yes, I guess the current one accepts all 3 ways.
okay, so then you don't have to worry about the stars for a lot of that. I know for other things though, like for sequential, you do have to do it, and I think for view, view still has to be parameters. But I mean, check. See if view works with the tuple, or if you actually splat the tuple. And that is the technical word. Star is the splat operator. Questions? All right. Thank you very much. And goodbye, stream. Just hit stop or.